Matt, if you could start the recording too. All right, so it's a great pleasure to welcome everybody back to the Symmetry Seminar in the new year. And our first speaker is Liang, and he'll talk about global quantum many-body theory. Please take it away.
Thank you. So first, I want to thank the organizer to inviting me to speak in this wonderful seminar series, which I've already enjoyed for a few months. Okay, so today I'm going to talk about the so-called global quantum many-body theory. I'll explain what the title means. How to turn? Okay. So the goal of this talk is to give a bird's-eye view of a global quantum many-body series and to bridge the gap among three communities, okay, the condensed matter theorists and the high energy theorists and the mathematicians, okay. So by a global quantum, what's going on here? Okay. By a global quantum many-body theory, maybe global quantum field theory or global condensed matter theory, depends on your taste, okay? I really mean a theory of a study all or many quantum field theories as their relations, importantly, and their relation as a whole. Okay, adding really, by the way, so I think the organizer of the seminar are mainly high energy physicists. So from now on, I will mainly use quantum field theory, okay, instead of condensed matter or quantum many-body, okay? Anyway, okay, so adding a relation to the set of all quantum field theory, we obtain the category of quantum field theory. So a category consists of a set of objects, okay? ABC are a label of objects. And the space of relations, which is also called one morphisms, okay, between two objects, okay? Very often it is denoted as this notation, okay? Usually it's a set or vector space. And the relation can be composed. So it also consists of the data of the composition of relations, okay? For high category, there are relations between relations. So they're called higher relations or higher morphisms, okay? So the first section of my talk is to talk about, all right, so if you want to study the category of a quantum field theory, you need to first know how to define the relations, okay? So the first section I will talk about how to define the relations. All right, so that's a natural question. What are the possible relations? I think the Euro definition of relation is given by domain wall between two quantum field theory. Okay, the higher codimensional domain wall define higher relations. This leads us to the higher category of quantum field theory, which is well known. Okay, a domain wall provides a physical realization of the mathematical notion of bimodules. Okay, because this picture, look at the picture, a domain wall between two quantum field theory automatically support a two-side action of the operators from the two quantum field theory. So that's a bimodule, okay? But I guess a physicist or mathematician should wonder, if you have this realization of a bimodule, but what if you have do you have another choices? Right, there's obvious choices, from mathematics point of view. Yes, so today I'm going to show you another one. Okay, so yes, we would like to introduce another type of relation, which really maps operator from one quantum field theory to another. Okay, this relation is natural because it provides a physical realization of the well-known mathematical notion of an algebra homomorphism between two algebras. Okay, so let me do this. Okay, before I do that, we needed some preparations. Okay, the term topological order in the following slides will be replaced eventually by quantum liquids. However, this is a notion which is hard to define, okay, at this stage. So therefore, for convenience, I will restrict our discussion to topological order first. Okay, so the definition says a topological order is called anomaly free if it can be realized by a lattice model in the same dimension. It is called anomalous if otherwise. Okay, that's our convention. I know high energy physicists sometimes don't use this convention. Okay, nevertheless, I will just use this terminology. Okay, I'll clarify in this definition. So I'll give you one example. So gapped boundary of a non-trivial topological order are example of anomalous topological order. Okay, I put a non-trivial here because if it is trivial, if a gap boundary is of a trivial topological order, well, then I will call this boundary anomaly free, one-dimensional lower topological order. Okay, that's the just convention of terminologies. All right. So the first non-trivial claim I want to make is called a unique bulk hypothesis, or you can also call it principle if you want. It says that a potentially anomalous ND topological order has a unique one-dimensional higher anomaly-free topological order as its bulk. Okay, so this is non-trivial statement. How to understand? I'm not going to give a proof. Okay, I want you to trust me, but I want to give you a partial explanation of this. An anomalous topological order must be realizable as a defect. Okay, in a higher dimension, but still finite dimensional lattice model, right? If it is not finite, I think if otherwise, it's safe to say such topological order does not exist. Okay, okay. Well, but such a realization is not unique in general. Okay, I drawn in this picture. So this defect AN is realized as a higher codimensional defect in some lattice model, okay, gapped model. But then what you can do is that you can introduce the following dimension reduction process. You drag this bullet to one side, and this becomes a cigar-shaped thing. Then you squeeze it to a line, okay? Although this realization is not unique. But our proposal is that, okay, after you do the dimensional reduction, this is unique. All right. So because it is unique, we can introduce a notation, right? I will just write the bulk as a ZAN, okay, because it's unique determinant, right? Okay, that's just a notation. All right, I'm going to use all this kind of, so yes.
I have a question. Is this an assumption or a requirement, or what happens if somebody shows you an example otherwise? Would you say that it doesn't move into this?
I think for topological order, Xiaogang and I, we have argument that this is true. We have just argument. Yeah, I don't know how satisfying is that proof is, but for topological order, I think it's true. But for general quantum field theory, I don't think it's true. Especially for those non-liquid, I don't think it's true. But for topological order, we believe it's true.
And what's the argument that this is always unique?
Yeah, the argument is a little bit complicated. Yeah, well, I'm not sure I want to go to the detail of that. Can I just propose a hypothesis?
Thank you. I'll look it up in the paper. Thank you.
Yeah, let me just let's just accept it as a hypothesis, which might be wrong in maybe in your cases. Yeah, but for topological order, the proposal is that this is true, and a lot of stuff is based on this assumption. Maybe you can accept this as assumption. Okay. All right, so I'm going to use this picture to represent the bulk. So you're going to always see this kind of physical configurations. So let me give you an example of the bulk. So D is a domain wall between A and B. D is a one-dimensional lower. So this is subscript is represent the dimension. It's an n-1 dimension. Okay, so D is a domain wall between these two. By the folding trick, you can realize the D as the boundary of a double layer system. Okay, so this double layer system is the bulk, and the B bar is the time reversal of B. Okay, well, of course, you can when A, B are the same, D can just be A, restrict to a one-dimensional lower submanifold. Okay, that's the example. Okay, now let me introduce the notion of morphism between two topological orders. So you have two ND topological order A and B. A morphism is a gapped domain wall. Okay, gapped domain wall Fn between these two. So draw this picture. This is An, and this is its bulk. Okay, and the Fn is a domain wall between. Is a domain wall, and Fn, when Fn is fused with An, you got Bn. Okay, if this is Bn, you can see that this have to be the bulk of B. All right, so this defines a morphism, and clearly, clearly this morphism can be composed, right? Because once you have F, if you have F, define a morphism from A to B. Okay, if you have a G, define a morphism from B to C. Now you can compose them obviously in this way. You just fuse these two. Okay, Gn and Fn. Gn and Fn are both domain wall. You fuse them, you got a domain wall between bulk of C and the bulk of A. Okay, so that's a composition. right? So this is, all right. So let me give you one example. Because you have a composition, you can easily show that there is identity morphism. Okay, so what is identity morphism? It is simply a domain wall, a trivial domain wall, okay, in the bulk of A, the trivial domain wall in it, just restrict to a one-dimensional lower submanifold. Clearly, this is clearly true, right? Okay, this is identity. I will tell you another one, which is slightly non-trivial, is 1n represent the I will use that to denote the trivial ND topological order. There is a canonical morphism from 1n to an. Okay, just using this picture. Okay, this 1n just means nothing. There's nothing there, and here is also empty, and this is an. Okay, you can see immediately that this defines a morphism. So it's called iota. Okay, it's called iota. All right, this is the second example. All right, now I'll give you a non-trivial example. All right, here is one trivial example, non-trivial example. It is a morphism from Z. Remember, ZA is the bulk of A, is one-dimensional higher. But I use N here represent the restriction of that to one-dimensional lower. So the picture is this. Basically, it is a A together with its bulk. Okay, together with its bulk. Can you see my mouse is moving? It's covered by the green line. But you fold it in the following way. Okay, look at the purple part. The purple part is the domain of the morphism. Okay, and the morphism is defined by the blue box. The blue box. The blue box defines the morphism. Okay, if you bracket them together, if you fuse this two part, you can see immediately that they reproduce A. That's the codomain of the morphism, a target of the morphism. Why that is true is obvious, right? Because when you do the fusion, it's the same. You can first unfold it and then fuse it. Then you got A. That's obvious. Okay, so this morphism called M, and you can, I will leave this as an easy exercise. You can use iota to do a composed morphism from AN. Okay, AN is equivalent to AN tensor product trivial phase, and use iota, you map to this one. Then you use M, you map to A. It turned out that this morphism is obviously just identity morphism. I will leave that as an exercise. This is trivial. Okay. But this condition, this equation represent a commutativity of the following diagram. Okay, you see this is iota identity M. Okay, look at this picture. This is iota identity A, and here's M. Okay, so that condition simply means compose this arrow with this arrow, you got this arrow. So it means this triangle is commutative. Okay, all right. So now we can state our first main results. The pair satisfy the following universal property, which is called the universal property of center. Okay, I'll explain in the next slides. Okay, it means if X is another ND topological order equipped with a morphism from Zn An to An, okay, Xn An to An, such that the triangle, a similar triangle, is commutative. Okay, then there is a unique morphism F prime from Zn to Zan. Xn to Zan, okay, such that the whole diagram is commutative. This is so-called the universal property of center. What does this mean? For physicists, perhaps if you first time to see category theory, this is really hard to understand what's going on. But let me put it in a simple way, okay? This theorem simply says the bulk is the center of the boundary, okay? What this universal property really means, this universal properties cover all the well-known notion of centers. For example, when A is a group, M is a group homomorphism. Okay, remember this M, this universal arrow is M is the group homomorphism. Then it recovers the center of group, which is a familiar notion to everybody, right? Similarly, when A is algebra, M is algebra homomorphism, it recovers the Eurocenter of algebra. Okay, let's try a few more. When A is a fusion category, M is a monoidal functor, then it recovers so-called dream field center. Okay, when A is a braided fusion category and M is a braided monoidal functor, it recovers the so-called Muir center. Okay, and many more. For example, the center of open string CFT is called, it's nothing but a closed CFT, and it is called full center. I should give some reference here, but I forgot. But more generally, in mathematics, there is a so-called generalized Deligne conjecture. It's called. It says that the En center of En algebra is an En plus 1 algebra. Perhaps it doesn't make much sense to you, but let me give you one example. The Drinfeld center is the example of E1 algebra. And the fusion category is the example of E1 algebra. Then Drinfeld center is the example of E1 center. And braided fusion category represents the E2 algebra. And its Milgauss center is example of the E2 center. Okay, so this is the main theme of Lewis' big book on higher algebra. Okay. Anyway, all right. Let me give you some what this result say in physics. Okay, the significance of the result, which means Bach is center of the boundary, which was known in many cases. For example, in 2 plus 1D topological order, we have recovered the well-known result. In this case, 2D topological order can be described by modular sensor category C, and is a gapped boundary. Assume there is a gap boundary. Can be described by a fusion category L, and in this case, we have the Drinfeld center of L equal to C. Okay, this is a well-known result, and using this result, we can also state the classification result for anomaly-free topological order. For example, is lead to the classification of anomaly-free topological order up to an invertible one by fusion N category with a trivial center. Because it is anomaly-free, that means the one-dimensional higher Bach have to be trivial. But one-dimensional higher Bach is the center. So the topological defect in the anomaly-free topological order, which we know they have a fusion product, consists of all codimension 1 defect. They can be fused, so they form a fusion N category. But the anomaly-free condition tell you that it had to has a non-trivial trivial E1 center. And there is a non-trivial theorem that says that okay, this can be equivalent to described as a braided fusion N category with a trivial E2 center. Okay, I won't go to the detail, but just tell you that this Bach equal to center is useful. Okay, it's useful in many cases. Not only it applied to topological order, this result also applied to gapless phase. Okay, the same proof can work for 1 plus 1D rational CFTs. Okay, this result reproduces so-called open-closed duality in 1 plus 1D rational CFT, which also says the Bach CFT or closed CFT is the center of the boundary CFT or open CFT. It has been known for a while. Okay. What does this mean? This means that the same proof apply for a certain gapless phase, right? So because of that, I could call those gapless phase such that above formal proof of boundary Bach relation works will be called a quantum liquid. Okay, so it's kind of a defining property of the quantum liquid. All right, but now it's good time to record a very well-known and a popular topic of topological symmetry. So you consider the following physical configurations, okay, drawn in this picture, and the pair F and C are recently was being called the topological symmetry or symmetry TFT of the final phase B. Okay, so from our point of view, this pair FC, or rather, this is a typo. Sorry, this should be F. Okay, or rather F alone, because this picture, according to our boundary Bach relation, our hypothesis, this C have to be the center of A. Okay, so maybe. So this have to be F, sorry, this is a typo, okay? So F alone can define a morphism from A to B. Okay, it should be viewed as object in a HOM AB, sometime use physics, mathematical notation is that. All right, using this point of view, you can answer certain questions that I heard from some Hannity people. They asked me, when the topological order can characterize the phase B completely? Well, here is the answer. From category theory immediately, because if you use this point of view, if you use the point of view that this defines a morphism, then clearly the representable functor COM B by letting A vary, okay, and this representative functor give a complete characterization of the quantum liquid B. This is nothing but the unique lemma in category theory. what if you're familiar with algebra geometry, Grothendieck's point of view, then this is nothing but the Grothendieck functor of point. So what I'm saying is that the study of quantum field theory is not that much different from the theory of algebra geometry of Grothendieck. Okay, that's a remark. All right, so maybe since people are really interested in topological symmetry, I will give a few more remarks. Why this looks like a morphism? Yeah, look at this following pictures. Okay, let me make the statement first. This definition of morphism coincides with the mathematical notion of a monoidal functor between two fusion categories. Okay, consider the following situation. Okay, A represent the boundary phase, represent the fusion category of the boundary phase. Okay, or maybe I should say the topological defect of codimension 1 and higher form a fusion category called A. Okay, and this domain wall also have topological defect form a higher fusion N category. I will call that F. Okay, I'm going to show you that this could be proved rigorously. Define a monoidal functor between A and B. Okay, B is obtained by fusing this strip. Okay, this. All right, and the domain wall between Z1b and ZB and ZA. These two concepts are equivalent because given the monoidal functor, you can define a fusion N category. How to define this fusion N category? So because there is a monoidal functor from A to B, that's equivalent to say there is an algebra homomorphism from A to B. Okay, then B is automatically equipped with the AB bimodule. Let the left A action take the left A action by simply map to B first, then act. Okay. Okay. So B is a AB bimodule, then you can define the category of functor of AB bimodule functors. Okay. And this is a fusion N category. Okay, this fusion N category actually is nothing but this domain wall. Conversely, if you give this domain wall, and you can actually get the monoidal functor from A to B, because you can see this clearly, right? Look at this picture. The fusion of two defect A1, A2, and you can see how it was mapped into D automatically, and you can see that this preserved the multiplication. Okay, so this is a algebra homomorphism, or in this case, it's called the monoidal functor. Okay, so that's why this is reasonable. All right, so I want to tell you that the same proof also works for gapless boundary of topological order, because the proof is so general. I said everything is the topological order, but it also works for a gapless boundary of n+1d topological order. Okay, it means that the mathematical description of the gapless boundary can be obtained from that of the block by solving the equation. If you know the mathematical description or categorical description of the block, then you can get that for the gapless boundary by solving this equation. Well, it's well known that the mathematical description of a 2+1d topological order is a pair, where C is a modular tensor category, which describes the fusion bridging property of anions, and the small c is a chiral central charge. And notice that the center of C is a double. Okay, C, this is a time reversal of C. Okay, so in some sense, the center of C is a C square. Okay, therefore, to some extent, the question mark is nothing but the square root of C. I want to remind the audience that the square root problems are important in history. Okay, for example, you have a square root of -1 and the square root of Laplacian, which is well known to be the Dirac operator. And for this equation, old mathematics is not very helpful in guessing the answer. Okay, however, the Mother Nature provided a solution. Okay, why? Because C can be viewed as a macroscopic observable of the bulk topological order in the long wavelength limit, right? Then this question mark have to be the categorical description of the macroscopic observable of the gapless boundary, clearly, right? So if you want to look for the answer, well, you just study what's going on the gapless boundary of the 2+1d topological order. All right, so consider a 1+1d worksheet of the gapless boundary of 2+1d topological order. Okay, what you can see, what you can have is shown in this picture. It turned out that all these macroscopic observables on this 1+1D worksheet form an enriched category. Okay, I will tell you why. First, it has topological defect lines, right? I already showed the topological defect line. And the A, B, C are labeled for them, right? Clearly, they belong to a labeling set S, okay? There are another data called MAB. MAB is a space of field living on the 1D defect junction, okay? MAB, okay? In particular, this MAB cover the defect field on the topological defect line because it means the space of field living on the TDL, the topological defect line, are labeled by A. It's just MAA. Okay, just MAA. All right, so MAB cover all the data. Oh, MAB together with the label cover all the data. Okay, but it's well known that these on the defect line you can have OPE of field. All right, but that's not the most general one. The most general one, most general OPE is you fuse a defect field in MAB with a defect field in MBC to obtain a defect field in MAC. That's the most general OPE, okay? And this OPE defines some kind of composition map, okay? Such that if you put all MAB with a double index together, they form a structure of a category, right? Because look, what's the category? Category is just a bunch of objects together with their relations. That's category. Okay. So we will show next that MAB is an object in abstract category B, and the composition map is a morphism in abstract category B. As a consequence, we obtain a B enriched category. The underlying set is S. Okay, I'll show you why. Okay. Okay, what happened is that among all the label, there is a trivial label. Okay, the label for the trivial TDL. Okay, the field living on the trivial TDL can live in a 2-cell. Why is that? Because what do you mean by TDL is trivial? It just means that the field living on the TDL cannot be distinguished from its neighborhood. That's why it's trivial. Okay, so it means MAA living on the 2-cell. Okay. All right. So a subspace or subalgebra of the field generated by energy moment tensor. This bracket is not a cat and bra. Okay, it is this generating set, the set subspace generated by energy moment tensor. This is a subspace of the M11. Is always transparent on the entire 2D worksheet. This is a requirement for conformal invariance. Okay, so that means this statement simply say all the TDL is conformal invariant. This is the minimal requirement. Okay, so I require all the TDL is conformal invariant. All right. Therefore, without loss of generality, we can assume that there is a subspace or subalgebra of M11 called V is transparent on the entire worksheet. I didn't introduce any assumption yet because minimum one is this is transparent on the entire worksheet. Okay, I just assume another is V is true. I didn't say anything about the V yet. But now I introduce assumption. I assume V is rational, so that mod V is an MTC, module tensor category. That's my assumption. Why I take this assumption? Because currently I don't know how to do irrational one. Yeah, that's just for convenience. Yeah, maybe in the future we can talk about the irrational case. Let's restrict to the rational case first. So V is called a chiral symmetry because it is transparent on the entire worksheet. So it's some kind of symmetry. Okay. And if the age is chiral, okay, and is defined mathematically by so-called vertex operator algebra, okay. If V is called a non-chiral symmetry, if the age is non-chiral, I use the age, sorry, I should use the boundaries for consistency. Condensed matter people call the boundary, in this case, called age, okay, sorry. So the age is, when the boundary is non-chiral, it is defined mathematical by so-called full field algebra. It's some kind of a non-chiral analog of VOA, okay? So that's the V. Since V is transparent on the entire worksheet, MAB is clearly a V module. Not only a V module, it supports action because V is transparent, right? It supports action of two-dimensional action. Okay, so this action is two-dimensional V actions. Okay, two-dimensional V actions. But it turned out that this is exactly how people define the notion of morphism, notion of module over a VOA. So, so that means this mod V, which denote the category of V modules. If I denote that as mod V, then I claim MAB is an object in V module. Okay, that's our conclusion. Okay. Next, this is also very important, but I won't go to the detail. Since V is transparent, okay, this V action also compatible, should also compatible with the OPE of MAB and MBC. So the OPE should compatible with the V action. What does this mean? Translated into mathematical language, it simply means this composition map is a morphism in mod V. Okay, this is highly loaded, but let me just take it for granted. Okay, if you translate carefully, what do you mean by OPE compatible with the V action? That's simply means this OPE is a morphism of mod V. Now you see everything is in mod V. MAB is in mod V. Composition is in mod V. So as a consequence, we obtain a mod V enriched category. And the Helm space of the enriched category is precisely MAB. Okay, so that's the enriched category. And moreover, it is not only an enriched category, it's an enriched fusion category because there is a horizontal fusion. The tensor product of the category is defined by the horizontal fusion of the TDL. You have two TDL here, right? Vertical lines. You can fuse them horizontally. Okay, that gives you a fusion of the object. Oops. Okay. It is convenient to introduce another abstract MTC, module tensor category B, and the equivalence between these two. Okay, then this pair encode the different enrichment. This is important because why? Phyllis might think, well, I already you got you convinced me this is a mod V enriched. Why you introduce another B? The simply because even you set B equal to mod V, you still can have Brady equivalence among them. So this phi can still be a non-trivial data. So then it's harmless to call the second one not as mod V, but as some abstract B. You can see why. Okay, but the point is, it turned out that all correlation functions and the OPE among the defect field can be recovered from the triple. I want to say this statement is again highly non-trivial. I think this is a fundamental progress in mathematics after Morris-Seiberg introduced the module tensor category, which almost end the study of a rational conformal field theory in physics. But the mathematician picked it up. They probably spent more than nearly 20 years to make it work. So this statement is highly non-trivial. Okay, it's rely on many, especially Huang's proof of rational CFT, rational VOA give you a module tensor category. You need everything in it, okay, in order to make sense of this sentence. Anyway, let me summarize. So as a consequence, we obtain a mathematical characterization of a gapped or gapless boundary of a 2 + 1 d top order. Is given by a triple, okay, and the V is called chiral or non-chiral symmetry. For chiral gap stage, V is a rational VOA, okay, of central charge C. For a non-chiral gap-based boundary, V is a rational full field algebra with a chiral central charge C. Okay, and when V is trivial, trivial as a VOA, trivial VOA, it describes a gapped boundary. Okay, the next data is the phi simply is the Brady equivalence between the mod V and B. Okay, but what is B? Now, what is the other data S? S is, remember, S is the labeling set of the TDL. Okay. It's a fusion category equipped with a Brady equivalence. Okay, this Brady equivalence will determine an enriched category by so-called the canonical construction. I won't tell you how to construct it, but the basically means that all the MAB can be obtained by so-called internal Helms. Okay, A and B are object in S, so they're just labeled in the labeling set. But you can define this thing called internal Helm. It become an object in B. This is so-called canonical construction. Again, it's a bird's eye view of the theory. I won't be able to explain to you what is the internal Helm is, but just trust me, okay? The data, there's no difference, right? They just to index, okay? All right, the punchline is this. Okay, remember that we want to solve the equation, right? We want to solve the equation for this equation. You see, we got the solution. Okay, the bulk is the center of the boundary. So the mathematical description of the boundary is enriched category. You compute the dream field center, you got the bulk. All right. So this theory also so this provides a solution to our the previous equations. All right, this is a little hard to understand it, right? So the next natural thing is to explain the examples, okay? But unfortunately, this example of gap boundary and the gapless chiral gapless boundary, okay, that's the natural thing to do, and also give you an example of non-chiral gapless boundaries or gapless edges. Unfortunately, it took a really long time, so I will skip it unless people ask questions. Okay, maybe I should postpone it to the question section. This will take quite a few slides. You can see a lot, right? But so instead of give you the example, which took too much time, I want to give you some geometric intuition behind it. Okay, so let me restate the previous theorem. A gap in the gapless boundary of the 2 + 1D topological order can be completely characterized by a triple. Well, it's pair. I just changed it in the last minute. Sorry. So it should be a pair. They contain two data. Let me talk about this data first. This data is an enriched category. It's called topological skeleton. Okay, why we distinguish them? Because this data is very special. It's categorical. The other one is not. Okay, so the other is called local quantum symmetry. I will view VOA as some kind of a local quantum symmetry. Okay, okay. The point is how to understand that theorem. The point is this topological skeleton part, this categorical part, can be or topological part can be completely obtained by a mysterious process. I will call we call the topological weak rotation. How to obtain this is very easy. Okay, now you consider the configuration drawn here. Okay, CC is the bulk. Okay, it is a 2 + 1D topological order. Now consider another BC of the same central charge, B another modular sensor category. Okay. Somehow they assume that they share a gap domain wall S. Okay, let me repeat, 2 + 1D topological order share a domain wall denoted by S. Okay, now you just do a fictional rotation to the time direction. Okay, this 2 dimension is a spatial dimension. You rotate it to a vertical direction. Well, assume it's a time direction. Okay, and you obtain an enriched category. I don't know how to define define the rotation physically. I don't know. Okay, but I want to tell you this is a very but somehow if you do that, you obtain an enriched category. Then this is exactly the topological skeleton of the gapless edge. The other 2 data have to be obtained independently. All right, that's how you should understand this. Not only that, when C is trivial, when bulk is trivial, we obtain a holographic duality between 3D series and 2D series, because this is a 2 + 1D. Okay, after you rotate it, because this bulk is trivial, because now the CC is trivial, you obtain a 1 + 1D series, which should be a categorical description of 1 + 1D CFT. All right. All right, let me give you some comment to the literature. Okay, the topological skeleton is contain all the topological data of the quantum field theory. Okay, because using this rotation, you see on the left it's purely topological. Okay, on the right, so this is also topological. Okay, so the underlying category S, S have a name in mathematics called underlying category, denoted as S. It was later called the fusion category symmetry or algebra hierarchy symmetry in physics literature. Okay, a lot of physicists studied this kind of symmetry. They call it the fusion category symmetry or even higher fusion category symmetry. Okay, but rarely have people to discuss this B, which is called the background category or ambient category of the enriched category. That's the name in mathematics. But in a special case, when C is trivial, B was later called the categorical symmetry when Ji Wenjie and Xiaogang introduced this. Okay, so it has a name. It's called the categorical symmetry. All right, that's the topological weak rotation. So I will shift the topic to topological weak rotation and quantum liquid and tell you what's going on there. Okay. All right. So we have this mysterious categorical weak rotation, right? But clearly this topological weak rotation have nothing to do with dimension. If you look at this, well, this is just a topological order in some dimension. This is topological order in some dimension, and this is a gap domain wall between them. It looks like this picture works for all dimension. Okay, then you do a topological weak rotation. It should apply. It should apply to all the dimensions. Yes, we're gonna propose that. Okay. We will call that topological potentially anomalous gapless quantum phase. Okay, we'll also describe by a pair. It's called quantum liquid. If the categorical topological skeleton part, what is a categorical skeleton? That just means summarization of all topological data of a quantum field theory. Okay, if this can be obtained by topological weak rotation, then I will call this phase quantum liquid. Okay, it's just a name. Okay, right. So that means you start with the in the spatial direction of n+1d topological order C, and with another B. Okay, you have a domain wall between them. All right, then you just rotate one B to a fictional, okay, a vertical direction. You might view it as a time direction. Okay, by that I mean, you combine B and S together to an enriched higher category that will define the topological skeleton. And as a consequence, this things, the dream field center of that is nothing but C. We have a full argument to show why this is true. All right, but I want to tell you that there is known that there are many examples in which the same topological skeleton can be realized by both gapped and gapless phases. There are examples in this slides. You're going to see that. All right, so that's my working definition of quantum liquid. Okay, if this doesn't work, then it's not called quantum liquid. All right. So a special case of this prediction is that a new type of holographic duality is based on the idea of topological weak rotation. Okay, it says that previously we have a box C which is non-trivial. Now let's just set C to be trivial. Okay, so there's no the other part. Okay, only have a boundary and n+1d topological order with a gapped boundary. All right, now you do a fictional rotation. You do a fictional rotation to vertical directions. You got to enrich the higher category. So let me do a little expansion of the discussion and see. So S is the category of topological defect on the boundaries. And its dream field center is the category of topological defect in the bulk, right? Because we show the bulk is the center. Clearly, the center axon S, center of S, axon S, right? The bulk, the defect in the bulk can fuse to the boundary, become a boundary defect. Okay, so there's an action there. Okay. Similarly, remember that we give a name of this, right? So after you rotate, you got a one-dimensional lower quantum liquid. Okay, this includes SPT phase, SET phase, and the spontaneous symmetry breaking phase, and also should contain certain gapless phase, as shown in the 1+1d rational CFT, with internal symmetry of certain finite type. Okay, so in this case, what is S? S is again a category of topological defect of this quantum liquid. But you can also, sometimes topological defect can be understood as super selection sectors of the state in the Hilbert space. Okay, and what is this? Now this is different now because there's no bulk anymore. So it turned out that this is a category of topological sector of operators. What do I mean by that? It's a space of non-local operators invariant under the action of a local operator algebra. Okay, it's different from the state. Okay, it's this topological sector of operators. And clearly, operator acts on state, right? So this also acts on S, which is compatible with this one. And then and this action naturally give you an enriched category by canonical construction, which is hard to define. I'm not going to talk about it. Okay. But anyway, one interesting fact is that the gauge symmetry in here on this side become global symmetry on this side. All right, I have another talk, more than 1 hour talk given on YouTube about the topological weak rotation, about this stuff. So I won't give full details, but I will give you one example. Okay, the topological weak rotation immediately recover the following well-known classification of 1+1d gapped phases with a finite onset symmetry. from the categorification of the gapped boundary of 2 plus 1D finite gauge theory. Okay, why is that? Because I showed here, I claim that the gauge symmetry here become global symmetry. So if you want to classify quantum liquid on this side with a global symmetry, well, you should consider gauge theory on the 1 dimension higher, and consider its gapped boundary. Yes, you immediately recover this. Okay, this is a well-known result. So 1 plus 1D topological bosonic gapped quantum liquid phase with onset symmetry are classified by the triple. And G is onset symmetry, okay, defined by finite group, and H is a subgroup, and omega is a two-co cycle. This is a well-known result obtained more than 10 years ago. Now we recovered, and we probably could say more. It turned out that the categorical skeleton of the 1D bosonic gapped phase associated to this triple is given by the enriched fusion category, okay, where AH omega denotes the Lagrangian algebra in this category, constructed from the pair. They are Lagrangian algebra, so by condensing them, you got the boundary. Okay, you condense the maximal condensable algebra, which is called Lagrangian algebra. You obtain a gapped boundary. So these things simply give you a gapped boundary. No, it's a notation for a gap boundary. I didn't explain what it is. Actually, this notation is the category of a right A module. A is a Lagrangian algebra, so you can define the category of A module. So it's a little mathematical. Let me forget. Let me do not go to detail. So it's a bird's eye view. So we kind of recover it and give us slightly more data, okay, because have the enriched category. I want to point out that a remark. We have a topological weak rotation as a proposal, right? It's just like a proposal. It's not a proof. So it turned out that there is an independent proposal and the proof of above holographic duality in all dimensions based on the idea of categorical symmetry was given in the literature. Okay. I also want to point out that there are more evidence of this type of holographic duality appeared in the literature. In a lot of literature. So recently, this 3D, 2D duality for finite abelian onset symmetry was also emphasized and studied by many people. Okay, I won't give a long list. I give a long list in my another talk on YouTube about this. But I suggest one of the paper by organizer have a rather complete list of the reference. Okay, so I recommend to read that list. I think that list is the most complete one because most of the reference does not contain the complete reference list. Anyway, except this one, I think. Anyway, all right. So, but this perhaps is still hard to understand, right? I give you one example, but I'm not sure I have time for this example. Maybe
I think the example might be useful.
Yeah, so this example is kind of well known for many people. So let's consider Ising chain, all right? Ising chain, and B and J are coupling constant, and X and Z are polymatrix, and U, the global operator is the global onset symmetry, Z2 symmetry. Okay, now you analyze what happened on this Ising chain on the space-time. So 1 plus 1D space-time. Again, you got something like this. And you will eventually you will see that the macroscopic observable on the 1 plus 1D worldsheet form again an enriched category. So let me explain the data. So you need to first ask what are the S? Okay, I will tell you what the S is. S are the label for TDL, topological defect line. But we know that in a symmetric case, okay, let me first study the symmetric case. That means GS equals 0. Let's study the symmetric case, okay? When J equals 0, in this case, there are two simple topological defect line. Because topological defect line from condensed matter physics point of view is just two particles, okay? But we know that the particle can also be understood as two superselection sectors of state, okay? In this case, there are two. One is trivial one, is the ground state. And plus minus is the eigenstate of X. Okay, so this is ground state. This is a trivial sector. There's another non-trivial sectors. It's well known. It's E charge. It's the Z2 charge. Okay, so one side of this is a minus. So this carry E2 charge. Okay, together they form a fusion category, a rep Z2. Okay. All right, what about B? Well, in this gapped case, remember B is a mod V from the CFT, right? So what replaced the chiral non-chiral symmetry B? There is a gapped version of this. We introduced a theory called the topological net of U-symmetric local operators. And the mod V of that exactly give you the category of sector of this net, which is category of sector of net. You can prove B is equal to this, the Drinfeld center of the REP-Z2, Drinfeld center of REP-Z2. This is also the modular sensor category associated to the famous 2+1D Tor code. Okay, but this is too abstract. Okay, let me give you a physical, easy way to understand it. Okay, so roughly speaking, there are just sectors of U-symmetric and non-local operators. Remember, I said before, it is a space of a non-confined non-local operator invariant under the action of symmetric local operators. Okay, you do a homework about that. It's very easy to see. I will denote the trivial sector of the U-symmetric local operators as 1. Okay, it consists of trivial operator, of identity operator, and a symmetric local operator. Z is symmetric because Z is not is anti-commute with S, but give a pair, it commute with U, commute with the symmetry. Okay, another one is M. It consists of a long string of X from negative infinity to a particular site I. Okay. And you can also use U multiplied. You get another long string to positive infinity. Okay. And another sector is called E. So this sector simply means because this operator is symmetric local. Okay. But if you multiply them all together for long string from I to positive infinity, you got a non-local operator, but still symmetric. Okay. So this is a non-trivial non-local symmetric operator. And by multiplying these two, you get F. It turned out that this 4 is nothing but a 4 particle in the Tor code. Okay, and you can study their action. You see what the action is. Okay, let me denote MAB is precisely the space operator that maps one sector A of state or TDL A to another sector B of state. Okay, so then I claim M11 is 1 plus N. So M11 is what? So M11 should consist of operator map vacuum sector to vacuum sector. Clearly, it contains the trivial sector, contains the trivial symmetrical sector, right? That's for sure. But it turned out that it also contains another one, contain M. Because why is that? Because M acts on the vacuum simply as an identity. Okay, it's invariant. It does not change the vacuum. So M11 contains two sectors. Okay, it's a direct sum of 2 sectors. Similarly, you can analyze the other. You can obtain this. It's non-trivial. Okay, all of them. You see, all of them is living in this B. Okay, all M11, M1E, MEE are object in B. So as a consequence, oops, we obtain an enriched fusion category, enriched in B. And in this case,
question here. I'm a little bit confused about the use of 3 different terms here, and maybe even more. One is the full Hilbert space of the system. Then you talk about sectors, and you also mentioned super selection sectors.
Yes.
When do you use which of them? And what? Yeah, how do you think of the distinction?
Here I only use the super selection sector. Or when I say sectors, I mean super selection sectors. Oops.
Now, the definition I know of super selection sector means that there is no local operator that maps us from one to another.
Yes.
Is this the case? Are you using the same definition?
Yes. Except here I require a symmetry. So I have to require U-symmetric local operator. So the operator have to U-symmetric.
But so if I have just act with the spin operator and it maps it to another state, is this a different super selection sector? I just a spin at one point.
Let's see. So for example, this one, this E particle will flip the screen, right?
It will flip. Is that
a
different sector or the same sector?
In this case, it's a different sector because I impose a symmetry. That's a very important question. Yes. So in this case, I flip the spin on the one side. it looks like it's a local operator, right? But because this flipping operator is Z, the flipping operator is a Z operator, right? So you can flip the plus minus is eigenstate of X. You can flip them from plus to minus by introducing a Z X on the side. But remember, the Z is not symmetric. Because Z is not symmetric, okay? Because Z is not symmetric, but it can be viewed as a symmetric non-local operator. So as a consequence, this can be generated by a non-local operator, but symmetric. So this creates a different sector.
So what you mean by sector is what's usually called charge sector rather than super selection.
I see. Sorry about that. I don't know the terminology. Sorry. Yeah, it's charge sector, I would say.
It's
yes.
not super selection sector.
Okay. Yeah. You're right. You're right. It's not. Sorry about the confusion.
Okay,
I don't know the term.
I'm glad you clarified.
Yeah. Yeah. This is so. I should say that the sectors are U-symmetric non-local operators. Yeah. I only talk about symmetric. So I didn't know there is a charge sectors. Yeah. Thank you for letting me know. Yeah. All right. Does it clarify it? All right. So let me summarize. So what we have done? We have done that the symmetric phase of icing chain is given by enriched category. So you do the similar thing for a symmetry breaking phase, you obtain another enriched category. Okay. It turned out that this TC is nothing but a category particle in the bulk of toric code, one-dimensional higher toric code. Okay. And the rep Z is the category particle on the smooth boundary of the toric code. And the vector Z2 is the category particle on the rough boundary of the toric code. So in summary, 2+1D toric code model with two different gapped boundaries, okay? And this two pairs. After you do the topological recrotation, you obtain two enriched category, which represent two phases in the icing chain. Okay, that's the example. All right, so do I still have time? Okay, I still have 5 minutes.
Yeah, you still have time.
Okay.
A few couple minutes.
All right. So this is the topological recrotations. Now I want to tell you, well, what we can do about this. First, I want to say that we emphasize it's a notation instead of just a holographic dictionary, because rotation suggests that all the geometric intuition should be preserved like a real rotation. For example, the dictionary, the holographic dictionary, should automatically extend to higher codimensional domain walls. Okay. It means that, all right, previously I said you have a pair of topological order, okay, or one-dimensional higher, and it has a gap boundary. You rotate it, you got an enriched higher category, okay? But now you can generalize this to all the domain walls, okay? Because look at this picture, okay? This AN is a boundary of something, and you have another BN of another, is a boundary of another things. And between A and B, you can have a domain wall. And this domain wall determine a relative bulk, in some sense. Okay, so I'll denote that as a Z1M. It turned out that this also some kind of center. Okay, so what I'm highlighting here, Z1M is a relative center of M. Okay, so this story continue carry over. All right, so then you can show that this pair, after rotation, right? So this picture, I for simplicity, this picture should be viewed in two ways. One is that you can view the vertical direction as the n spatial direction, or you can view them as in the time direction after the topological recrotation. Okay, the two pictures. All right. So as a consequence, okay, not only extend to higher domain walls. It turned out that this holographic map is also compatible with the fusion of domain walls. Okay. So what do I mean by that? You can first rotate this part. Okay. You can first rotate this part, this pair, to time direction. You got an enriched category. Okay. Then you rotate this part. After you rotate, everything is rotated. Okay. You got this part. And you also got this one, okay, which obtained from this pair, okay? All right, so then you fuse them. This is equivalent to you first fuse them in the spatial dimension. You fuse them first in the spatial dimension, then rotate to the time direction. You got another enriched category. So, all right, this equality simply tell you from category theory point of view, simply tell you that the notion of topological weak rotation is functorial. Okay, you can first rotate, do the fusion, or you can do the fusion first, then rotate. They're compatible. Moreover, I want to tell you this fusion formula can even be further simplified by this one. So this superscript have this formula. Let me explain what the meaning of that. So this formula is given here. Okay. It means that, oh, okay, so this part is the relative bulk of M, and this part is the relative bulk of N. Okay. Now you fuse their bulk. Fuse their bulk, you got this one. Okay, you got this one. You fuse in the bulk. Okay, then you can also do you fuse them on the boundary. Then consider the relative bulk. It turns out that they're equal. What does this mean? This is another functoriality. Okay, so this theorem, this result simply says the following: the boundary bulk relation of topological order can be reformulated in a rather complete way as a center functor. Basically, it says that, okay, consider ND topological order, okay, n plus 1D topological order, and this is their gapped boundary, okay. We obtain a functor because the boundary, for each boundary A, you obtain, you take a center, okay. For each domain wall, which is one morphism, you take a relative center, which is defined by this. So the relative center can be explicitly defined as AB bimodule functors from M to M. Okay, this is the mathematical definition of this relative bulk or relative center. All right. Not only this is a functor, it turned out that when n equal 2, this functor is, you can prove that this functor is a monodal equivalence. For higher dimension, it's not a monodal equivalence, but still very powerful statement. But for 2 plus 1D is a monodal equivalence. Yeah. Okay. Then you combine these two. So this previous formula is a combination of functoriality of topological weak rotation and that of center, right? And turn out this formula gives the boundary bulk relation or duality, if you want, for all gapless quantum liquid. And the formula provide a formula for computing the fusion of two wall CFT. Let me look at the time. How long I already over time. So let me okay, so in the current state of high energy people, as far as I know, people like to compute the following things. For example, you want to compute, you have a CFT1, CFT2, CFT3. In between, you have domain wall CFTs. You want to know how to fuse them together, right? Yeah. So I already used the internal Helm to represent the wall CFT or domain wall between wall CFTs. Okay. You want to know how to compute them, right? By supplying all the detailed defining data of CFT1, CFT2, and their domain wall in this picture. I won't be able to go to the detail of why this data define the precise data. But no matter what, the conclusion is once the precise data was provided, this fusion can be computed in a precise way. You obtain a precise formula in terms of enriched category. But I think physicists don't have an intuition about this. Well, what the internal Helm really is. This bracket is called internal Helm. Oops, what's going on? Oh, sorry. All right, so our theory actually turned out to, so I'll give you another example. So our theory allows explicit calculation of all possible fusions, at least on the level of topological skeletons in all dimensions. Physicists, I believe they like to compute this, right? I'll give you one example. So consider a 2 plus 1D topological order, another 2 plus 1D topological order. And this vertical, it represents a gapless domain wall. Okay, it's a gapless domain wall. This is fictional. It's not. It's obtained by topological weak rotation. Okay, so it's an enriched category. So by fusing this two domain wall, what do? Very naively, you just fuse a superscript with a superscript. Okay, that's what you do, and you fuse the underlying category with the underlying category D and N. Okay, you got MDN. All right, that's very easy. Okay, if you apply this to the following situation, squeezing a 2 plus 1D topological order with a gapless edge and the gap domain wall in green color, gap domain 1 between the topological order. You squeeze them into a 1 plus 1D system. Okay, you should get 1 plus 1D conformal field theory, right? But this formula automatically tells you how to compute the conformal modular invariant conformal field theory, because what the modular invariant conformal field theory must live in the 2 cell. What live on the 2 cell is precisely M11. As I said before, 1 is a trivial PDL, trivial topological defect line. Okay, M11 live in the 2 cell. You simply compute M11. But what is M11? M11 is the internal harm. Can be computed using categorical language. So after you got the enriched category, this M11 is done. It's fixed. It's computable. And this way, you recover all the modular invariant modules conformal field theory. This proof a well-known result of 1-to-1 correspondence between the domain wall of C and the modular invariant partition function, modular invariant CFT within C box tensor C bar. This is a well-known result, but now you have an explicit explanation. All right, so I guess I don't have time for. Let me just quickly say what it is. Because of everything is a dream field center. So look at this picture again. This is a center of that, and this is it's a relative center of M. So everything is determined by this purple box, right? So physicists like to compute certain defects, fusion rules of fusion defect between within a topological order or within a quantum field theory. But you can do, you can ask yourself, what if I put everything together, put all different kind of quantum field theory together? Or in this case, let me restrict the quantum field theory to whatever I call the quantum liquid. Okay, I denote the quantum liquid, n-dimensional quantum liquid by this notation, and that of a topological skeleton in this notation. You ask yourself, can I compute this category altogether? What do I mean by compute? Compute means that you associate, you determine this category by some identified with some things, and that something can be computed, can be constructed, can be determined very easily. So yes, indeed, you can. The result is this. So this category is very simple, and this dot is nothing but is called slice category. This dot is bullet is nothing but the tensor unit of the n vec, n+1 vec. What is n+1 vec? It can be constructed using so-called delooping of vec, or even delooping of from complex number. So it's a very natural, simple way of a simple construction. Okay, was given by Galto and Johnson-Fried in a beautiful paper of theirs. Okay. All right. So we got. So it turned out that to compute all of them together, it's much easier. It's much easier than compute the fusion rule of defect in a particular phase. All right, I won't have time to tell you that. This is almost the last slide. I want to tell you that previously we said there is working definition of quantum liquid, and topological skeleton can be obtained from topological weak rotation. What about the other data, the missing data? Yes, there is we propose a series of the missing data of the local quantum symmetry. It's a little complicated, but it's a mathematical theory of, called topological nets or defect, which is generalizing the mathematical theory of conformal nets and defect in 2 dimensions. All right, so let me summarize. Okay, so the global QMT or global QFT is a program studying category of quantum field theory. A new notion of morphism between quantum field theory lead us to the boundary Bock relations, okay, which says Bock is center of the boundary. And the mathematical theory of gap-based boundary, that's the further lead us to that, and lead us to a unified mathematical theory. Oh, I didn't tell you this. From topological weak rotation, yes, it lead us a unified mathematical theory of this. Okay, and the boundary Bock relation also including by including higher codimensional defect, it give you a functor. Okay, and also tell you how to compute category of quantum liquids. Okay, and the theory of topological weak rotation, local quantum symmetries. The outlook is that similar to the fact that the category theory once revolutionized algebraic geometry by Grothendieck and his school, we believe that it will also revolutionize the theory of quantum field theory, phase transition, and perhaps quantum gravity as well. Thank you very much. Sorry, I go over time.
Okay, thanks very much. It was a nice talk. Are there any other questions? You can just unmute you. That's not. Please unmute yourself.
Hi, thank you for the very nice talk. I had a question about you had this working definition of what a quantum liquid is.
Yeah.
Are there examples of stuff that would not be quantum liquid in your definition, and how would I see that?
Yeah. So well, what we suspect is that what's in the quantum liquid, because this holographic dual, we have an independent proof of this using a categorical symmetry. So so we believe that the quantum liquid at least include SPT phase, SET phase. These are gap and the symmetry breaking phase. Okay, but for what gapless phase should be included in quantum liquid, as far as we know, rational 1+1D CFT should be in there. But for higher dimensional one, we don't have explicit example, but we believe those rational one or those nice one, you know, Ising or I mean, certain nice CFT in higher dimensional should be included in its quantum liquid. That's as far as I know. But all the gapped quantum liquid, I think that all the gapped quantum liquid can be covered by this SPD phase, SET phase, and spontaneous symmetry breaking phase. For gapless one, yes, I think this need a further study. We're working towards it, but right now I have very little to say about it.
And do you know whether fracton phases would be
I
outside
think
of this in some sense?
Oh, I think it's outside this because when we write the paper, we have a struggle about the name of the quantum liquid. And we don't have a good name for this. Later on, we decided to call it liquid because we have this intuition that the liquid should be some kind of soft, so you can bend it. You can. There are many ways you can twist it without changing it. So this suggests certain finite property and a certain fully dualizability of this. So for fracton, for non-liquid, I believe it does not work. That's my intuition. I don't have proof, of course. Yeah.
And for gapless theories that are not CFTs would also have a similar problem, or
yeah,
non-rational
for irrational theory. Yeah, I think irrational theory.
already.
For example, fracton have the problem, right? If you the ground state degeneracy scale as a size of the system, right? In that case, it's break the finite intuition in our mind. I think it's not finite in some sense. Yeah.
Thank you.
Because we, in order for this theory to work, we require very strong, or maybe the fully dualizability of the theory. So a defect can always bend, a twisted, a wiggle, you know, you can always do that. So this requires very strong duality. This duality requires certain finiteness. I don't think a non-liquid to satisfy this. That's my intuition. Of course, I don't know. I never studied fracton. In this way, yeah.
Okay, there's a question from Nati Cyber.
Yeah, so at the beginning, you talked about this gap boundary for the gap bulk. And I asked you whether it's unique or not. Can you clarify how things work in the simple example that we have? So spontaneous Z2 symmetry breaking in the bulk, and we have directly boundary conditions on the boundary. So there's really nothing on the boundary, but there are two states in the bulk. So how can you go through your reasoning in that case?
I'm not sure I can use, because I have trouble to understand Dirichlet boundary condition. That's good, but I wonder, is this explanation? I hope this explanation might help. For example, if you consider 2+1D topological order, if you regard a gapped boundary of this topological order as something obtained by performing a anion condensation, I'm not sure this.
This is way too complicated.
This document work for your case at all.
Yeah, this is much more complicated. I'm interested in a much simpler example. If you want to be in 2+1 dimensions, that's fine. Let's be in 2+1 dimensions. And we have broken phase.
Yeah.
We have Ising in the broken phase, so there are two ground states.
Yeah.
there's a question of whether we call this topological order or not, and different people use different definitions, but let's take this system. It exists.
Okay.
And now boundary conditions that all the spins are up.
Yeah.
So I would say that the boundary is trivial, and the bulk has two states.
I think well, if you do in the Ising chain case, I don't know, but if you do, oh, I don't know how to interpret it as a boundary, but if you do a topological recursion backwards to toric code, if you do that for toric code, then you can see why the boundary determine the bulk uniquely, because in the toric code, you know, there are 4 particles. And on the boundary, there are 2 types of boundary. One's a smooth boundary, another rough boundary. And one of the boundary, M particle condensed, the other one is E particle condensed.
Yeah, that's an example. So I propose it. I'm asking about another example, which has far fewer moving parts, right? It has only 2 states in the bulk.
Yes.
Nothing. It's completely trivial on the boundary. So I you take the same Ising spin as you had. It's a finite chain.
Are you saying you asked me for Ising chain? Can you also have the boundary bulk relation by considering the boundary of Ising chain? Is that what you're saying?
That's a way of phrasing it. Yeah.
So yes.
The bulk
Unfortunately, I have a slide for this. But in our paper, yes, we explained that if you have a boundary, if you consider the boundary phase of the symmetric phase, you can have 2 types of boundary condition. One is preserve the symmetry, another is break the symmetry. These 2 cases, you can do the same analyze. You can show that they form an enriched category, and this enriched category, you can also define the notion of center, which is exactly give you the bulk enriched category. So in that case, this still works. So the boundary enriched category again determine the bulk enriched category, which is summarize all the microscopic observable in the long wavelength limit.
Again, you're answering a much more difficult question than the one I asked. At the very beginning, you said that the boundary uniquely determines the bulk.
Yeah.
Okay. So let's take this case where I take fixed boundary conditions. So there's only 1 state on the boundary because I have fixed boundary conditions, and there are 2 states in the bulk.
Yeah.
Now, is this an example of what you described, how the bulk is uniquely determined? Yeah. Okay. Yes. So now let's do the same thing with Zn with arbitrary n. Then I would say there is still only 1 state on the boundary, but now we have n states in the bulk. So the bulk is not uniquely determined by the boundary unless you add more assumptions.
It's not that well, I think maybe the difference happened on what do you mean by define the boundary? But because when we check, when we work out the boundary, we work out all the super selection sector on the boundaries, which contain the many information of the bulk already. Because we need to analyze what is non-local operator respect to the boundary. In that case, you recover an enriched category, and its center is giving you the bulk. So the way you formulate it looks like the bulk is not unique. But what I'm saying is that if the boundary, if you do it in our way, it will determine the enriched category in the bulk uniquely by computing the dream field center. Can I give you more detail of this afterwards? I can send you the paper because I deleted the slide. I have this slide. Yeah, I have the slides to explain the situation in my previous slide, but I deleted it because I don't think I have time for this. So I deleted it. I didn't know that people could ask this.
I'm sorry for being so slow.
No, it's okay. Yeah, it's I think it's non-trivial. It's highly non-trivial. Yeah.
Actually, I don't know whether I can answer this question. Is that I wonder whether nothing means like in the bulk, you have a symmetry breaking phase. You have a 2 state, spin up, spin down. Then the boundary, you may also have spin up, spin down. So then the sense that the boundary spin up determine the bulk spin up state, and the boundary spin down determine the bulk spin down states. But the bulk spin up, spin down is a degenerate. And so one may wonder, maybe the boundary, the spin up, spin down state also degenerate. And but the degeneracy of the boundary spin up, spin down somehow involving the bulk. What I mean is that when you say degeneracy, we mean the direct sum of spin up, spin down of a boundary. But in this case, when you do the direct sum of spin down of spin up of a boundary, then it's automatically involve a direct sum of spin up, spin down of the bulk. So this is this may be new situation. Usually, when you have a boundary degeneracy, we have a same bulk with a two degenerate boundary. That is spin up, spin down boundary are degenerate, but the bulk is the same. But in this case, when boundary are degenerate, we have to include the degenerate bulk. So that's kind of a funny situation.
Xiaogang, thank you for clarifying it. But
yeah,
there are different questions you could ask. You can ask, can you put the boundary with all possible boundary conditions, or I'm more limited. I have a problem with fixed boundary conditions that I'm given, and I would just want to discuss this system.
Yeah.
I don't see why I should sum over all possible boundary conditions.
You don't need to.
What you're saying is that the claim was that given a theory on the boundary, the bulk is unique.
Yeah.
I thought that that means that I can put on the boundary whatever I want. So I put a trivial theory on the boundary.
Whatever the boundary you impose, this boundary somehow know the bulk.
I think what you do, I think what you're doing, you define the information on the boundary such that your hypothesis is correct. You feed more into the boundary to make the bulk unique. But the way you normally formulate the boundary, you don't put this information in, and then the bulk is not unique.
Yeah, probably that's maybe the correct summary. In a sense, the boundary include its neighborhood somehow.
Yes.
That's maybe the
So if you put into what you mean by the boundary, the neighborhood of the bulk, it's not surprising that the bulk is uniquely determined, because you put a little bit of the bulk in the information.
Exactly.
If you set only the boundary, then it's clearly does not uniquely determine the bulk.
Yeah, but I think that's the key point. When we define the boundary, when we use the macroscopic data to define it, we always include the neighborhood of that.
Oh, thank you.
No matter what the boundary condition you choose a boundary condition, given anyone you like. By including a neighborhood of the bulk, there are way to recover the bulk by using the Drinfield's.
That's not what's normally meant by boundary conditions.
I guess
when you solve differential equations with boundary conditions, you specify the function of the boundary, and you don't say anything about the derivative of the function or what the function does in the neighborhood of the boundary. You just specify what happens on the boundary.
Yes.
But if you change the definition, then I have no problem.
Yeah. But
I think boundary is not a boundary condition, but boundary probably here means some kind of a fusion category with some data which correspond to a boundary. That's probably the meaning.
You see, when you choose a boundary condition, that's the same as the PDE, or you choose a boundary condition. However, when you analyze this boundary as a boundary phase, when you analyze the boundary as a boundary phase, no matter what the boundary condition you choose, by including a neighborhood, you always determine the bulk. That's what I mean. So in the paper, we analyzed the different kind of boundary condition. Yes, they will produce a different boundary phase, but no matter what the boundary phase eventually you end up with, its bulk is uniquely fixed.
I don't know whether another point of view may be helpful. That is, when you view boundary, here boundary probably is a boundary effective theory. And then the boundary effective theory may have anomalies. So this anomaly inside the boundary effect theory correspond to bulk. So that's maybe the another way to see this.
Right. So view the bulk phase as the the anomaly of the boundary phase.
I mean, there's just a comment in the chat by Bai, which I think maybe clarifies this, right? That really you were thinking in terms of the symmetry category that the boundary theory has, that is uniquely defined by this process. So in this 2+1 dimensional case, the lines that can live on the boundary, right?
Yeah, I think for people study topological symmetry, they also use this argument, right?
Yeah, but it's usually not that the theory is determined uniquely, but it's, you know, the symmetry structure, so all the topological defects, and also the anomaly, right? Because it could be, as in your pictures, you had sort of the sandwich picture that there's an anomaly theory attached, and then you collapse this interval, this gap C, and then you get a theory, and from this whole process, you determine the symmetry plus its anomalies. The simplest example is in the bulk, you have a BF theory or some higher dimensional Dyker-Witten theory, and you put boundary conditions on that, and that determines the symmetry of the boundary theory.
Yeah.
That's maybe more intuitive, or at least that's how in high energy physics we would think about this.
Maybe another remark I could add is that the boundary condition could be really, really arbitrary. For example, in this situation, you give a gapless A, you can stack arbitrary anomaly-free phase to a gapless A, and without changing the box C. The C is not changed. But in this, in this way, it looks like the boundary conditions could be really arbitrary. But still, the categorical theory tell you that this is still consistent because by stacking one of one dimension lower, have the same dimension as a gapless A in this picture here, it won't change A because the bulk of that stacked theory is trivial. Yeah. Even though they change the boundary condition, but it don't change the bulk. It changes the boundary theory, but don't change the bulk.
Okay, so I think I don't see any other questions. Let's maybe thank Liang again for this nice talk.
Thank you very much.
And we probably should stop the recording.